Welcome to Module 4, covering asphalt binders for the Quality Assurance Certified Technician Program. I am Jason Walensky, the moderator for this section. I am the Director of Construction Materials Testing and Research at the Heritage Research Group. So let's go ahead and talk about the overview for this module concerning asphalt binders. We're going to cover what asphalt binders are. We're going to discuss how they're manufactured. We're going to review the grading system. We're going to discuss how these asphalt binders are tested and certified. We will review some safety protocols. We will identify some best practices for storage and handling, and as well as sampling. And then at the end of the module, we're going to talk about specific gravity of asphalt binders and perform some temperature volume calculations. Hot mix asphalt is a combination of aggregates that are bound together with asphalt binder. The performance of hot mix asphalt is affected by the properties of the aggregate in the asphalt binder, as well as the proportion of each. Properties of asphalt binders is critical to ensure that the performance of the road meets expectations of the road agencies. Testing of these binders is traditionally not done by our contractors, but it's important for us all to understand the properties and how they impact the mixtures placed out on the road, as well as understanding handling and sampling for success. Asphalt is a black cementing material that varies from a solid to a semi-solid at room temperature. So take a look at the pictures below the text. You can see that over time, the softer asphalt actually begins to flow, if you will, out of the pen can. That is because asphalt both has solid and liquid components to it, even at room temperature. Asphalt is also extracted from crude oil. It's produced in the distillation process of these crude oils in an oil refinery. And it's important to know that not all crude sources are the same and not all refining processes are the same. And this results in differing properties of different asphalt binders used in road construction. The schematic shows the different temperatures at which molecules are recovered during the distillation process in a refining operation. So as the temperature is increased, the refinery recovers the lighter molecules. So first is the gas cut, followed by the gasoline cut, followed by heavier cuts of the crude oil, including kerosene, diesel, and gas oils. The asphalt binder is the heaviest part and is the residual of the bottom, or the bottoms often referred to during the distillation process. This schematic shows all the different parts that would contribute to the manufacturing of asphalt. You can see that the crude oil would be pumped out into the oil well, goes into the field storage pumping station, and then off to the refinery. So you can see how the light distillates would be processed off, followed by the medium and heavier distillates. The residual, or the asphalt cement, then goes into that process, followed by the different types of asphalt that we could cut out of it, including cutbacks and asphalt emulsions that are used for various road construction processes. The next topic to discuss is the performance grading system for asphalt binders. Back in the late 80s, the Strategic Highway Research Program began, and the outcome was specifications also known as the SuperPave specifications for both hot mix asphalt and performance graded binders. This was a new way for us to identify and develop and specify asphalt binders used in road construction. Previous to this, there were ways to just grade binders based on viscosity or penetration. But the SuperPave performance graded asphalt binder program really enabled agencies and practitioners to specify and develop binders that would meet properties both at high temperature conditions realized in the summer, as well as maintaining flexibility at the low temperatures in the winter. And to meet those requirements, the PG grading system was established. and our PG binders used in hot mix asphalt construction all have this kind of nomenclature to identify the grade of asphalt binder used. The first number represents the maximum pavement design temperature. 64 is a common number used in many of our asphalt binders used in Indiana. The higher the first number, the stiffer the asphalt binder is. So oftentimes on higher volume projects, we will use a 70 or a 76 minus 22 type binder. The higher the number at the beginning, the stiffer the asphalt is. The second number, and in this example, minus 22, represents the minimum pavement design temperature. It's important that even at low temperatures, the asphalt binder has the ability to relax and contract. If the binder does not have sufficient low temperature properties, the pavement may exhibit low temperature cracking, which will result in a distress in the pavement. So the farther negative the second number, the more flexible that asphalt binder is at low temperatures. For example, in Indiana, our typical low temperature is minus 22, whereas some colder climates like Minnesota or Canada, they will specify minus 28 or minus 34 asphalt binders. Likewise, farther south, in Arizona, for example, they may specify a minus 16 asphalt binder. Those numbers are identified through a number of testing protocols established to set the stiffness and the low temperature properties. And we're going to discuss some of the properties and testing protocols associated so that we develop a better understanding of how these numbers are established. We're going to discuss about the aging protocols used to simulate aging that's realized in the asphalt binders in real time. We'll talk about the dynamic shear rheometer, which is used to measure stiffness. We'll talk about the bending beam, which is used to realize and understand low temperature properties. We're going to talk about viscosity, which is important for storage and handling. And we're going to talk about flash point, which is a critical safety measure of the asphalt binder. The properties of asphalt change over time with aging. Aging occurs both under high temperature conditions and in situ in the field as the pavement ages under the sunlight and begins to oxidize. So as we try to characterize these asphalt binders, specifications call for us to simulate the aging that the binder goes through during both production and in service on the roadway. So one way we try to identify the short-term aging, or the aging that's realized by the asphalt in the manufacturing process of hot mix asphalt in our hot mix plants, is to use a rolling thin film oven. So in this apparatus, we'll put a sample of asphalt in the glass tubes, and it undergoes similar aging to what the binder would do in the asphalt plant. That binder is then recovered and looked for stiffness to ensure enough sufficient flexibility and stiffness after this aging protocol. In addition to that rolling thin film oven, the asphalt also undergoes long-term aging. It undergoes this long-term aging in an apparatus we call the pressure aging vessel, or PAV. Now, the aging protocol used in this test simulates approximately 8 to 10 years of life in the pavement. So we're trying to forecast or predict the stiffness of that asphalt in 8 to 10 years under traffic, under sunlight, and under the environments. And after that asphalt is aged, we use a dynamic shear rheometer to evaluate the high temperature stiffness as well as the intermediate stiffness of the asphalt binder. We want to ensure that the asphalt binder has sufficient stiffness as to prevent the risk or minimize the risk of rutting in the pavement. We also want to ensure sufficient intermediate stiffness of the asphalt binders to make the asphalt pavement more resistant to fatigue cracking. So this is the test that identifies the first number in the PG grading system. For example, the 64 or the 70 or the 76 that we commonly see with our Indiana asphalts for road construction. To identify the properties or the low temperature properties of the asphalt binder, specifications call for the bending beam test. So in this test, after both RTFO and PAV aging, a tiny beam of asphalt is actually manufactured and then is actually put in this apparatus to understand the stiffness of the asphalt and the ability of the asphalt to relax at low temperatures. So it is from this test that the asphalt achieves its -22 or -28 rating for the specifications. And it's critical that asphalt has sufficient flexibility at those low temperatures to provide the asphalt pavement overall to have enough flexibility to withstand the freeze-thaw cycles and the significant drops in pavement temperature that are frequently seen in Indiana winters. The rotational viscosity is also tested by the asphalt binder manufacturers, and this test is real critical for both the high temperature storage and handling of the asphalt binders, as well as the pumpability and the ability for us to pump it through the hot mix plant and get good workability in the asphalt drum. Another test that's of importance is the flash point test. The flash point is the temperature at which a particular compound gives off sufficient vapor to ignite in air. And it's very important and critical that asphalt binders are always stored below the flash point temperature. This temperature is also typically supplied by the binder manufacturer. According to the Asphalt Institute, typical flash points for conventional hot mix asphalt binders are 230 Celsius or around 450 Fahrenheit or higher. So it's really important that we store asphalt binders in both our tanks or in labs well below this flash point from a safety concern. Which brings up another another example of some safety issues, particularly when our lab personnel are handling and storing asphalt, liquid asphalt, both in the lab and on our facilities. So a couple things we're going to talk about are both the storage and handling hazards, in particular burns, hydrogen disulfide or H2S, and identify the risk around asphalt binder fumes. As always, it's important to understand traffic, both in our plants and on job sites, to make sure that we have the necessary understanding of where the vehicles are to maintain that everybody gets in and around the plant in a safe manner. So for storage and handling solutions, it is recommended to be aware of burn hazard locations. Always use designated walk areas in the asphalt plant areas. Always look out for construction traffic. It's important to avoid tank vent openings, particularly for H2S buildup. We always want to try to stay upwind of asphalt fumes if possible. And when sampling, it's critical to wear the necessary PPE. And it's highly recommended to wear long sleeve shirts and pants, as well as gloves and face and eye protection to minimize any risk from asphalt burns from splashing or spilling. And as always, follow the established safety procedures identified by your safety personnel at your plant. So what happens if a burn does occur when handling an asphalt binder? Immediately apply cold water. Do not try to remove the asphalt. Always have a physician examine the burn area. For a great reference, the Asphalt Institute has developed a video for first responders. Pocket safety cards and posters are also available and recommended to have in your labs to ensure that everyone's well educated on what to do in case of a burn with asphalt. Hydrogen sulfide, or H2S, is a buildup of vapor space of asphalt in the asphalt binder tank. It's often identified as a rotten egg smell. Some of our modified asphalt binders, for example our PG76 type binders, may have higher levels of hydrogen sulfide. It's always critical to keep your face away out of man waste to minimize exposure to H2S Always stay upwind of the hatch and try to avoid breathing fumes. If overexposure does occur, immediately move to fresh air. Administer oxygen if breathing becomes difficult, and start CPR if breathing stops. It is also critical to have exposed persons see a physician immediately. Storage of asphalt binders is the next topic we're going to cover. Asphalt binders are sampled for compliance by INDOT at hot mix asphalt facilities. Some critical storage issues always are related to or could come from contamination. And contamination can occur from a number of different sources. Contamination can occur by combining different binders together. It can also be a contamination from fuel oil. Another storage issue to be cognizant of during plant manufacturing is overheating or extended heating of the asphalt binders. This will create additional aging and stiffening of the asphalt binders at the facility. It's imperative always to follow storage and handling guidelines from the asphalt binder producers. INDOT collects asphalt binders for quality control at HMA facilities. Here's an example of an asphalt binder storage tank. And sampling is imperative and important for representative samples to ensure that a sufficient sample is being used and collected and tested to identify the properties of the asphalt binder being used in the hot mix asphalt. So let's identify some potential sampling issues. It's recommended to avoid sampling from the top of the tank if possible. It's highly recommended to use only clean containers. This would minimize any risk of cross-contamination with other binders or other fuel type sources. It's recommended to allow 1 gallon of asphalt binder to drain out of the sampling spigot before sampling. Again, this would minimize any contamination into the new sample. And it's also recommended to seal that container immediately after sampling. Some other best practices in sampling and labeling issues is to always clean the container on the outside if asphalt is spilled. This helps make sure a clean sample, especially if the sample needs reheated, and it helps with identifying labels. We always want to label containers clearly. We want to also identify and label the can. We don't want to label the lid because oftentimes the lids get discarded or switched or moved around. So best practice is definitely to sample the can that the sample is included in. And as always, follow the safety procedures established by your plant personnel. The next part of our presentation is going to look at the specific gravity of asphalt binders utilizing the pycnometer method. Traditionally, this is performed by the material supplier, and the specific gravity of asphalt binder is usually listed at 60 degrees Fahrenheit. The specific gravity of asphalt is the ratio of the weight of a volume of material to the weight of an equal volume of water, both at the same specified temperature. So for example, if the specific gravity of the asphalt sample is greater than 1, it is heavier than water. Likewise, if the specific gravity of the material is less than 1, it is lighter than water. It's also important to know and recognize that asphalt binders expand and contract in volume with temperature. So specific gravity at a specified temperature provides a yardstick for the temperature volume calculation. So the temperature volume relationship is a conversion between the mass and volume, and it's quite necessary. Binders are typically sold by mass. They're sold by tons, not by volume. But in hot mix asphalt, volume is more important for the volumetrics in the asphalt mixture design. So why is it needed? It's needed for the metering of asphalt by volume at the plants, and it is also key and critical in determining inventory. So let's go ahead and do a temperature volume example for asphalt binders. In this example, a storage tank contains 15,000 gallons of a PG 64-22 at 295 degrees Fahrenheit. The specific gravity of the asphalt binder is 1.012 x 60 degree at Fahrenheit. Again, this number is typically provided by the asphalt binder supplier. In this example, we're going to calculate the tons of 64 minus 22 to the nearest first decimal place. So step one is to convert volume from 295 to 60 degree Fahrenheit. The first step that we need to do is determine the volume correction factor. And in our manual, we're going to look at page 3-13 to look at the column N multiplier for this temperature. And we can see that at 295, under column M, that the multiplier factor is 0.9204. Moving forward, we're going to take the volume at 60 degrees Fahrenheit is equals to the volume of the actual temperature times the conversion factor. So we're going to take the 15,000 gallons and we're going to multiply it by the 0.9204 to get the answer, which is 13,806 gallons. The next step is to convert to tons. So we've already identified the top, the 13,806. We will then multiply by the specific gravity as well as the weight of water to convert to mass, and then we're going to divide by tons. When we execute that problem, we achieve the answer, which is 58.2 tons. Another note of interest is that the voluntary asphalt supplier certification program, this is permitted for suppliers to manufacture and ship to HMA facilities. It requires instruction of proper storage and handling by specification through INDOT. And ultimately, it's important to know and realize that the goal is to have long-lasting asphalt pavements. It's critical to have all of our teammates on the job have a good understanding of how to produce top quality asphalt mixtures so that we as an industry can achieve these long-lasting pavements. The QC/QA program is a critical part of that success. And top qualified, top certified technicians are typically and often the difference between long-term performance and early failure. So I encourage everyone listening that participates in these programs, please do not ever underestimate the role you play in this grand scheme of building top quality roadways.